under the sea, under the sea. Darling, it's better down where it's wetter. Take it from me. Up on the shore they work all day, out in the sun they slave away, while we devoting full time to floating under the sea.
Good morning, class. So, as I told you last time, we're going to be discussing the case study on the energetics of life on the deep sea floor. Did you both read it?
Yes.
Yeah. Good. Okay. So let's start with a little bit of introduction to get you familiarized with the topics that we need to know for this. For this experiment, the researchers took measurements at all different depths of the ocean. However, the main focus was on the benthic and the lower aphotic zones. The benthic zone is defined as the substrate of the ocean, and the aphotic zone is all of the ocean that does not receive enough sunlight for photosynthesis. Primary production is when inorganic materials are converted to organic materials or biomass. Usually this happens through photosynthesis, but the deep sea floor receives very little or no sunlight, so it does not have organisms that do photosynthesis. As a result, productivity is very limited, as shown by the purple regions on this picture. However, changes in temperature could be affecting production. Global warming is the cause for a rise in temperature across the globe by a process called the greenhouse effect. Humans are introducing much more carbon dioxide into the atmosphere. This CO2 traps heat radiation from the Earth and does not let it escape into space. Therefore, temperatures are rising all over the world.
In this experiment, they use metabolic theory of ecology, MTE. This predicts the effects of body size and temperature on metabolism through considerations of biochemical kinetics. Specifically, they used MTE to examine the relative roles of carbon flux and temperature in influencing metabolic rate, lifespan, body size, and biomass. This map displays the sampling locations of bacteria, meiofauna, macrofauna, megafauna, and mollusks used in the study. At the level of the organism, mass and temperature play primary roles in controlling individual metabolic rate and turnover. As shown in the first graph, metabolic rate and mass have an indirect relationship. As mass increases, metabolic rate decreases. However, the second graph shows temperature has the opposite effect on metabolic rate. As temperature increases, metabolic rate also increases. The first graph displays the relationship between mass and turnover. Like the relationship between mass and temperature, mass and turnover have an indirect relationship. As mass increases, turnover decreases. In the second graph, temperature and turnover follow the same indirect relationship, however, at a far less dramatic rate. In this graph, the x-axis is measuring the natural log of flux, and the y-axis is measuring the natural log of biomass. As you can see from the line of best fit, carbon flux, not temperature, is a significant predictor of biomass such that higher fluxes lead to greater average body sizes in a locality. From this graph, you can see the lack of a role for depth on mass-specific metabolic rate, implying that metabolic rate is independent on pressure. This can be related to the fact that organisms experiencing high in situ primary production from hydrothermal vent and methane seep have rates comparable with other deep-sea organisms.
Although the deep sea floor is one of Earth's largest ecosystems, we still know very little about the transfer of energy through this ecosystem and the importance of its conservation. As we learned in this experiment, temperature puts a significant limitation on the body size of deep sea organisms, which in turn affects the overall biomass of a population. This means that subsequent climate change will have an impact on the density of deep sea organisms. The effect of this change in biomass on other ocean ecosystems is unknown, making it crucial that we begin to better understand the processes of the deep sea floor. This experiment also proved that carbon flux in the form of particulate organic carbon is directly related to patterns of biodiversity in the deep sea. This variation in biodiversity with carbon flux may be attributed to competition between species or niche overlap. Taking these two factors into account, climate change has already begun to affect deep-sea ecosystems. Over the past century, global phytoplankton production has decreased approximately 1% per year, which has decreased the amount of carbon available on the deep sea floor. Also, the deep oceans now store 16 to 89% more heat. These changes could greatly impact the biomass and biodiversity of deep sea organisms. Now that this experiment has proved that climate change impacts deep sea ecosystems, it is important that further research be conducted to understand the consequences of forthcoming change in the deep sea.